In this video, we're going to look at some basic concepts that will be important in connection with our study of second order differential equations in Chapter 2. We'll start off with an example of a second order differential equation. Example 1, y double prime minus y prime equals 0. And we'll use this differential equation to introduce a trick that won't work in general, but it will work on a problem like this where you only have the second derivative and first derivative terms. If you just let y prime be denoted by v as your first step, basically the reason we're using v here is we're thinking of y as being position, then y prime would be velocity. With that notation, then y double prime is going to be v prime in your differential equation, which was originally a second order differential equation for y, becomes a first order differential equation for v. So this is one example of a technique called reduction of order, because we've reduced the order of our second order differential equation. We've turned it into a first order differential equation. And this is a first order differential equation that we've seen before in Chapter 1. So the reader can solve that using their favorite method. I'm not going to include those details in this video. The solution of that first order differential equation turns out to have that form. V of x is c1 e to the x. And once we have that, we can go back to y and recall v is equal to y prime. So then y prime is c1 e to the x. And we just can integrate that then to find y. And we get our general solution. Y is c1 e to the x plus c2 is our general solution of the original second order differential equation. Notice, as is typical for just about every problem you're going to see in this chapter, when you start off with the second order ordinary differential equation, your general solution, which we found here, is going to contain two constants. Usually you'll have two initial conditions that you will use to determine the values of those constants. We'll look at an example shortly where we do that kind of thing. Here's another example of a second order differential equation. There's a little bit of a discussion about that differential equation where we're thinking of k as being essentially any non-zero constant. There's a little bit of a discussion in the text about that, and the solution turns out to be that, to have that form, the general solution. Y is c1 e to the kx plus c2 e to the minus kx. Again, there's a discussion, more detailed discussion of that differential equation in the text, which I'm not going to go through in this video. The main thing to notice here is, again, we had a second order differential equation, and the general solution contained two functions, in this case e to the kx and e to the minus kx, and two constants, c1 and c2, which will be determined from initial conditions. Almost all of the differential equations that we'll be looking at in this chapter have this general form of a general second order linear ordinary differential equation. Our differential equation is linear, just like in the last chapter, meaning that the differential equation is linear as a function of y and all of its derivatives, which this certainly is. It's perfectly fine to have functions of x, essentially any arbitrary function of x, theoretically at least, can be solved as a second order linear ordinary differential equation. Most of the time, and most of the applications we'll look at, you're going to actually look at a special case where the coefficient functions on the left-hand side are all constants, A, B, and C. And when we're in that situation, your right-hand side still does not need to be a constant in general. Your right-hand side, which we're denoting by f of x, can be basically anything, but those problems are a lot easier to deal with when all of the coefficient functions on the left-hand side happen to be constants, and we'll be doing a lot of work with equations of that type later on in this chapter. Another little bit of terminology is the fact that we always call our differential equation homogeneous whenever the right-hand side is equal to 0. In terms of the physical applications, usually your right-hand side function is something like an external force or an external voltage or something like that that's external to the system that you're studying. And physically, it would be the case that if that external force or external voltage was 0, then the right-hand side of the differential equation would be 0. And that makes it easier to deal with. We will look at a lot of examples later in the chapter where the right-hand side is not 0, but earlier in the chapter we will look at, for starters, we'll look at situations where the right-hand side is equal to 0, and that'll be generally easier to deal with. So that's basically what we are looking at in chapter 2. Here's another example where we've now included two initial conditions. We have a second order differential equation with two initial conditions given. So we call a problem like that an initial value problem. That's what you're usually going to be dealing with in applications. An initial value problem is an ordinary differential equation together with one or more initial conditions. In chapter 1, we were mainly studying first order differential equations, so we had one initial condition. Here, since we're studying second order differential equations, we have two initial conditions. Assuming what was stated on the previous slide, that the general solution has this form, we can take the derivative of that with respect to x and use the chain rule on both terms, and we get that expression for the derivative. At that point, we have an expression for our solution containing C1 and C2, and we have an expression for the derivative of our solution also containing C1 and C2, and we have two initial conditions here now, which we haven't used yet, and we can use those initial conditions now together with the expressions that we just found for the solution and its derivative. When we plug in x equals 0 in this equation, we just get C1 plus C2. When we plug in x equals 0 into the second equation, we just get 5C1 minus 5C2. So that gives us this system of two equations and two unknowns for C1 and C2. I'm assuming that my students have had some experience with solving two equations and two unknowns, so I'm leaving out the details on that. You can use your favorite method. I would usually use elimination in a problem like this. You could use elimination or substitution or technology to find the solution of that 2x2 linear system. And you're starting to see the connections here between this topic and linear algebra. There are a lot of connections, and I'll be saying more about that as we go along. So once you find your solution of that linear system for C1 and C2, you plug that back into the expression that we started off with. I'll make that a big round blob, I guess. Back up here, you take those values for C1 and C2, which we found by solving that system, and you plug those back into that blob expression, and that gives you this expression, which now is the solution of the given initial value problem, meaning it satisfies the differential equation and it also satisfies our two initial conditions.